All right, so maybe there's some problems you've been looking at, what you want to ask questions on. I'll do some of these that I'm gonna put on the final exam, like for instance, number 2 will be on here. Number 1 might be on there, but definitely number 2. I want you to be able to solve right triangles. That's one of the most important things of the course when you get out. That's what you do all the time in other courses. Solve the right triangle. With the following measures. We'll do 2B here, let's say, with A equals 8 centimeters and side B equals 3 centimeters. And I gave you this drawing here. I'll probably give you a drawing on the final exam just to make sure there's no questions. But the assumption is always that A and B are legs. Doesn't matter where you put each one. But C is the hypotenuse. All right. So how can I solve the right triangle? Given 2 measures, other than angle, it determines a unique right triangle, right? And so there's 3 things to find left. Remaining, you have a right angle in these 2 measures. You have to find 3 more. So what you can do here is I'm given these 2 sides. Whenever you have 2 sides, you can always find the 3rd side by the Pythagorean theorem, right? Here's the Pythagorean theorem solved for C is square root A squared plus B squared. So memorize the Pythagorean theorem if you forgot it. A squared plus B squared equals C squared. Here it is solved for C. So it's the square root of 8 squared plus C plus 3 squared, the square root of 73, and I can run that on the calculator. You'll get approximation. Calculator. Square root 73 gives me 8.544. So I didn't say where to round it. Just put at least 3 digits if I don't say where, so I can tell they knew what you were doing. And then it's centimeters because the other side was in centimeters, right? Some of these I might say round to so many decimal places. If I say round to 3 decimal places, that means 3 places, 3 digits right of the decimal point. Right? The next digit is 0. I would just say, so you round it to 4. If this next digit is 5 or greater, you round it up. All right, so there's that one. Given 2 sides, you can always find the 3rd side by the Pythagorean theorem. In a right triangle only, don't use it for the oblique triangles. There you need the law of cosines, right? Now, once I have that, I can find the angle, an angle by relating 2 sides that I know to an angle by a right triangle relationship. You can use law of sines or cosines too, but because it applies to any triangle, but it's longer that way. It's faster just to use right triangle trigonometry. We'll say, for instance, using the numbers I was given, tangent of beta goes opposite B and alpha goes opposite A. Tangent of beta is B over A, right? Relates the 2 numbers I know I've given to the one I want to find here, beta. So let's see, B over A is 3 over 8. So what is beta? If tangent beta is 3/8, then beta is arctangent. How do I know it's not maybe 180 minus the arctangent? Or something like that, so, or arctangent plus 300 plus 180 degrees or something. In a right triangle, when you have a trig function equal to number, the angle is always just the inverse trig function. The reason is that in a right triangle, the 2 angles are always acute, right? 90 degrees is here, these add up to 90. These are always less than 90, so they're always just the inverse trig function. It's easy. If tangent beta is this number, beta is the arctangent. That's it. Arctangent, make sure it's in degrees mode. I probably need to change this. That's in radians. Change this now. Yep. Let's try inverse tangent 3/8. I come up with 20.556. Zero. If I round that to 3 decimal places, then I call it 20.556. Degrees, right? I'm in degrees mode. And then finally, once you have one angle in a right triangle, the last one is always 180 minus the other two, or more easily, these two are always complementary. It's 90 minus the one you have in a right triangle. So 90 minus 20.556 gives me 69 .444, right? Degrees. All right, so there's number 2. I'm going to ask you a problem like 2A or 2B. I'm going to give you two measures in the triangle other than angle, which is only one, and ask you to solve the triangle. I'll give you a side and a side like this, or a side and an angle. Solve the triangle just like this. One of the most important problems in trigonometry, even though it's not all that hard. But you can use the Pythagorean theorem to get the sides, the sum of the complementary angles theorem for right triangles to get one of the angles, and a trig relation relating two knowns and one unknown to find the other measure. Okay. You need to do that in your higher math courses. So everybody will get 100% on that one, hopefully. Here's an interesting one. We have applications of trigonometry besides triangles. For instance, for A and B, A says find the area of a sector of a circle. If the radius is 3 inches, and the central angle is 20 degrees. How do you solve that one?
Is that R equals sine, or is that R equals?
Oh, R equals 3 inches. Sorry about that. It looks like sine, right? Yeah, 3 inches. You memorize the formula. A equals 1/2 R squared theta. Need to know that for the final if I ask you this question. This is one of the ones here I might ask you that. Maybe not, maybe. If you forget it, how can you figure it out for this one? We did the proof of this before, right? You can say the area of the whole circle is pi r squared, right? Memorize that from geometry. Then what's the area of a sector, a slice of pizza, right? Maybe if I measure out 20 degrees here and a measure of 3 inches along the radius. Well, it's just pi r, so now I'm interested in this area A here. Is the area of the circle times the fraction of the circle subtended by the central angle is 20 is theta divided by 2 pi, right? Theta radians out of 2 pi in the whole circle gives you the fraction of the circle times the area of the whole circle gives you the area of the sector, A, right? Well, now the pi's cancel nicely, and you get 1/2 r squared theta. So you can derive the formula if you forget it. It's just fraction of circle, theta over 2 pi times the circle area formula. This isn't too bad a formula, so I'm just going to take 1/2 r squared times theta. Except something's wrong. What's wrong with that answer? You get something off on that.
Degrees.
Yeah, it's in degrees. This only works in radians, right? It assumed theta radians out of 2 pi radians, so I have to put theta in radians. Well, convert the 20 degrees by multiplying it by pi over 180. This is one of the other major concepts of the course. Convert degrees to radians, multiply by pi over 180. That way the degrees on top cancel the degrees on bottom. And I get radians here. Now, 3 squared is feet squared, right? It's 3 feet, quantity squared is feet squared. And then I've got radians, so the area is now feet squared radians. Radians is unitless and fall out, so you've got square feet. But good, it's an area, right? You can kind of check yourself like that. But let's see, 1/2 times 9 times 20 pi over 180, right? That's what I've got left. Oh, wait a minute, 20 over 180 is 1/9. Multiplied by 9, these cancel, right? 1/9 and 1/9. And so I just got pi over 2 square feet. How about that? Well, that's A. What about B? Find the arc length subtended on the same circle. Same circle. Well, now what do I put? The easiest formula is semester, but you have to know it, right? S equals R theta. You can figure that one out by taking the circumference. Call S the arc length. It's the circumference, 2 pi r around the circle, times the fraction of the circle subtended, theta over 2 pi. And the pi's cancel and the 2's cancel, and you get r theta. S equals r theta. So you can figure that one out too if you forget. But just memorize it. S equals r theta, easiest formula semester, is 3 inches times 20 degrees. And once again, it's in degrees, then your units will be feet degrees. That's not what you want. Well, if you put feet radians, and radians is unitless, you can drop it off and it'll just be feet. So we need to convert this to degrees by multiplying by pi radians. Leave the units off if you want, over 1 for every 180 degrees. All right, pi radians straight angle equals 180 degrees straight angle. Now let's see, this is 3 times 20 over 180 is 1/9 times pi. Oh, it's just pi over 3. Degrees cancel, radians you drop, and it's 3 feet here. So it's pi over 3 feet. It's how much chord would go along S, this arc length along the edge. S is the arc length here subtended by 20 degrees. A is the area here of the slice of pizza subtended by 20 degrees in the circle of radius 3 inches. Okay. That's what you need for these. A equals 1/2 r squared theta needs to be memorized or figured out. Better to memorize it. S equals r theta. Another major concept, and I'll ask you one of these, you'll have to do it somewhere. Maybe I won't ask you the same question, but it'll come up in one of the other questions. Have to be able, in any ensuing course, be able to do trig functions of special angles exactly. So that's what this question is, 5a, let's say. Find exactly by hand. And by the way, your fancy calculators will do this exactly for you also if you put them in exact mode. You can check your answers on this. Check your answer, right? Find exactly, didn't say exactly, but that's what I meant. I'll probably put that in the exam. Find exactly cotangent of 150 degrees. Cotangent isn't on your calculator. To check with your calculator, you take 1 over tangent. You have to know the reciprocal identity. But check it that way. But I can do cotangent of any special angle. This is a multiple of 30 degrees, right? Special angles are multiples of 30 or 45. How do I know it's a multiple of 30? It's a multiple of 10 because it ends in a 0. And then 15 is a multiple of 3, so it's a multiple of 30, right? You can look at it and see. Well, this is a special angle. Special angle, I can always do in the unit circle. I just draw the special angle and I say, well, 150 is almost 180 a straight angle, so it's something like that. What's left? Well, if this is 180 and this is 150, then the difference is 30 degrees. So the reference angle, we say, is 30 degrees for this reference triangle I get by dropping a perpendicular to the x-axis. Oh, if it's 30 degrees, a special triangle, right? Well, it will come out whenever you have a special angle, you get a special triangle here, or it'll be on an axis. If I got a 30, 60, 90 triangle, we memorize those two triangles, and you absolutely have to know those for the test. These two triangles, right, that fit right in the unit circle. You need the 30, 60, 90. Has sides, the small side opposite 30 is a half, the medium side opposite 60 is square root of 3 over 2, and the long side is 1. With long side 1, it fits in the unit circle. Here's 1 half, square root of 3 over 2 here. This point there has coordinates negative square root of 3 over 2 since that went left, plus 1 half since that went up. And here's a major concept out of trigonometry. On the unit circle, if you take an angle in standard position, the point where it intersects has coordinates, cosine, sine of that angle. So this is the cosine of 150 is minus square root of 3 over 2. And the sine of 150 is 1 half. If I'd asked you for cosine or sine, you'd be done. You'd put this number or this number, right? So that's a major point when you get out. The point of intersection on the unit circle is cosine and sine of the angle that got you there in standard position. Since I want cotangent, I can either say it's x over y. That's one way of defining it. We define that at the beginning of the course. Cotangent is x over y in the unit circle, just like x is cosine, y sine. Or you can say it's cosine over sine. Either way, it's this one over this one, right? Cosine over sine or x over y is the same thing, right? X, y. So it's minus square root 3 over 2 for x, 1 half for y. And when you have the same denominators, you can cancel them. Or if you have the same numerators, don't cancel the numerator with the denominator. Be careful, right? But these two cancel because they're both denominators. I get minus square root 3 over 1 or just minus square root 3. There it is. The cotangent is exactly the minus the square root of 3. Don't put minus 1.732 from your calculator. That's an approximation. You'll probably get 0. Right? I don't want you to plug it in the calculator to get it. I want you to figure it exactly. This number goes on forever without a repeating decimal. It's called true rational for that reason. You just, anywhere you round it won't be exact. We'll leave it like that. Be able to find the trig function of any special angle exactly, and then check it by taking 1 over tangent. You can do this one decimal and this one in decimal if your calculator doesn't do exact, and see if they look the same. All right. 6. This is not a major concept, but it's kind of tricky, I think. And it's not bad, it's easy, but it's kind of tricky. Find angular speed. That's like in radians per second or degrees per second. Let's say for this one in radians per second. That's the rate at which an angle changes. It's like linear speed is distance per second, like feet per second or miles per hour or something. In radians per second of an object that travels at linear speed along a circle. "12 feet per second if the radius is 5 feet. I should have handed out another copy of these practice problems in case you don't have yours from last time. Anybody want another copy of the practice, the problems we're going over here? If you get any questions, ask them. Here is this one then. You just have to memorize the formula. V equals R omega. Once again, one thing I like about mathematics, if you can't remember that, you can figure it out. This one follows naturally from that basic equation, S equals R theta, right? Arc length equals radius times angle subtended. If you divide each side by t, S, the arc length is distance, divided by time is the speed, right? Distance over time is velocity or speed. Positive distance is both. All right. And then theta divided by time is what we call angular velocity, usually written omega. So when the equation is v equals r omega, you can just figure it by dividing this one by t, right? Angular change per unit time is angular velocity. Distance per unit time is linear velocity, right? So we use this equation and we put in the numbers. It says the linear speed is 12 feet per second. The radius is 5 feet. And the angular velocity is what we're trying to find. Oh, that's easy. Divide by 5, and you got omega equals 12 fifths. 12 fifths what? Well, 12 was feet per second, right? 5, you don't have to put these units in. 5 was feet, and the feet cancel, and you get 12 fifths per second. What is 12 fifths? Oh, let's just leave it as 12 fifths. It's 2.4, right? 2.4 per second. Per second, what does that mean? I just point this out that in your literature, you sometimes find angular rates of change in per second. What does that mean? Radians is unitless. It means radians per second, right? You can think of omega in radians per second. That's what we wanted, right? So I'll put radians per second or 1/seconds, and either way is the way they'll write it in industry. There's the angular velocity. It's easy as that. V equals r omega, but it's kind of tricky to do. Like velocity is distance divided by time. Angular velocity is angle divided by time. Here's an important concept too. We've got to be able to do graphs and in particular waves. I told you before, I think, in vibration analysis and all engineering and physics courses and so forth, and lots of other courses too. Everything is done by breaking it up into a sum of sine waves. You know, if you get a jumbled wave like this, you write it as a sum of sine functions. And that's how they do the analysis of these things. Voice patterns or whatever, a note struck on the piano or whatever. And so you have to know how these waves work. Suppose I do 7a and I say sketch the graph. You have to be able to sketch all 6 trig functions. So remember I said I might change the functions. I might change cosine to cosecant or something, right? I'll be able to do all 6 of these Miller graphs. Y equals minus cosine 2x plus 3. Sketch it over one period. How do I do that? Remember this topic? I told you we don't have to do anything but this review. It's plenty to do all by itself. Lots of stuff, right? How do I sketch a trig function? The only kinds we're sketching are y equals a trig function bx minus c plus t. We run in that form. Minus 1 cosine 2x minus 0 plus 3 is a cosine in this case, bx minus c plus t. Right? So there it is. A must be minus 1, B must be 2, C must be 0, and D must be 3. You find the 4 letters by looking at it, and then you use that to get the 5 properties. Right? What are the 5 properties? They're amplitude for sine and cosine, or stretch factor in any case. The other ones, since they're not waves, you just call them stretch factors. This is also a stretch factor. So the amplitude is always absolute value of A. Amplitude is always positive. It's not negative 1. It's 1 here. Right? Period. The period is always 2 pi over b, and you just have to memorize this, except for which functions? Not 2 pi over b. Tangent and cotangent. Remember, the natural period of tangent and cotangent is pi. So when you stretch them by a factor 1 over b, it's 2 pi. It's 1 pi over b. So all these functions, these 5 properties will be the same, except that for tangent, cotangent period, it'll be pi over b instead of 2 pi over b. Otherwise, it's the same graphing techniques for all trig functions. You start with their basic form, and you figure out these 5 things. In this case, we've got 2 pi over 2. So the period is pi, repeats every pi units. Then the phase shift, or horizontal shift, is c over b. You just have to memorize these. So memorize phase shift is c over b, period is 2 pi over b, amplitude is absolute value of a, and you can do this part. And then there's a vertical shift. This one you should already know from algebra. It's just whatever number you add on the end moves it up or down by that amount. Vertical shift is always d, therefore, right? And then the flip, if a is less than 0, then it, right, cosine becomes minus cosine, flips the y-coordinates negative upside down. This one does flip since a is less than 0, right? A is negative 1. Now, the stretch factor of 1 means it's actually unstretched, right? If you multiply the thing by 1, it's the same height it was before. All right, and then flip since a is less than 0 in this case. Vertical shift is d, was 3 that we added on the end. So you memorize these things. Flip if a is negative, vertical shift to d, phase shift c over b, period 2 pi over b, amplitude absolute value of a. Then you can sketch it, any trig function, just from its basic graph, use these properties to sketch it. For sine or cosine, it's a wave, right? Something that goes on forever without, on forever repeating the same form. So let's see, how do you do it? The easiest way is to find the shift point. I wish books would emphasize this more. The shift point is just the phase shift. In this case, I didn't finish it. It's 0 over 2. Reading from here, 0 and 2. 0. So it's 0 shifted horizontally. That's easy. And vertical shift of 3. So I go to the point 0, 3, right here. And everything centers around there. If you do that, that's the easiest way. Because now what happens is the midline goes through that point, right? And then you go up 1 amplitude up. A equals 1. Amplitude, let's say, equals 1. Up. And amplitude down. And so these are the guidelines. So from the center, from the shift point, you go up by the amplitude and down by the amplitude to find the guidelines for the wave. Isn't that easy? And now if it's a cosine, then it starts at the top if it's unflipped, the bottom if it's flipped. Remember that? Because the basic cosine, just y equals cosine x, starts at the top and goes like that, right? So if you move it over, the origin goes to the shift point, and it'll start at the top if A is positive, and the bottom if you flip it upside down, A is negative. The sine goes through the origin, so it'll go through the shift point, up if it's not flipped, down if it's flipped. So that's what you figure. If it's a cosine, we'll start here at the bottom guideline when A is negative. So cosine starts at the bottom guideline, just because it's the flipped cosine with the origin shifted to here. Cosine starts at the bottom guideline when A is less than 0. Below the shift point. Now I've got that part. The shift point is at x equals 0, so I go over 1 period. What's the period? It's pi. So maybe I'll put it here or something. Doesn't have to be scaled the same on both axes, I don't care. You should have the same y value 1 period later. So there's another point, 1 period, pi over. You put the same y value. Now it completes 1 period, so you do 1 wave, one period of the wave, up to the top, all the way back down to the bottom. There's one period of the cosine. Bottom to bottom, or top to top, or middle to middle, having gone up and down and back to the middle. Here it is, and now, one important point in all textbooks is you can find 5 exact points on this, right? What are the exact points? Well, there's the shift point, the point vertical from the shift point, which is at 0, 3 in this case, 0, 2. The bottom guideline here is 0, 2. And one period later, it has to have the same y-coordinate, so this must be, since I moved over pi units, it must be pi 2. There's a second exact point. Then what's this point here? How do I find that one? It's just halfway between, right? The peak is halfway between the valley. So halfway between 0 and pi is pi over 2. And then it's at the top guideline, so I put 4, right? This is 2, 3, 4, because the shift point is at 0, 3, and then 1 unit down, 1 unit up, makes these 2 and 4. And then this one, right, where it crosses the midline is halfway between this x-coordinate and this one. So halfway between 0 and pi over 2 is pi over 4. And it's on the midline, so it's 3 for the y-coordinate. This one here, halfway between half pi and 1 pi is 3/4 pi. And then it's on the midline, so it's 3. There it is. There's 5 exact points. Every book expects to be able to do that, right? I hope this pulls it all together so you feel comfortable with what we learned in trigonometry here. There it is. Any questions on that one? Find the 5 letters from the equation. Use those, 4 letters. Use those to find the 5 properties. Start at the shift point. Unflip cosine starts at the top guideline. Flip starts at the bottom guideline. Sine goes through the middle, up if A is positive, down if A is negative. Draw one period by going over whatever the period was. Find these 5 exact points. You can sketch it very nicely. Okay. Here's a good one. Solve a trig identity. That's another thing we had to do. This is one of the harder problems of the course, I think. 8A. Solve cosine 2 theta plus sine squared theta minus 1/4 equals 0 for all possible theta. Be careful on this. I might say all theta between 0 and 2 pi, or I might say all theta, and then you have to put your 2 big pi in the end, right? How do I solve a trig equation for all possible theta? There were some rules of thumb that are nice for these. Rule 0, we gave it 0 because it started later after rules 1, 2, 3, was to get one angle. Right? If this is 2 theta and this is theta, I don't know how to solve it. So I get one angle, and how can I find this, reduce this to one angle? Well, if I've got 2 theta, I can use a double angle identity. This is why you need to know the identities, right? We need the quotient identity and the other one. Now we need the double angle identity. You need to know the sum and difference formulas, the double angle identities, and half angle identities. I don't think I mentioned those earlier. Cosine 2 theta is cosine squared theta minus sine squared theta. Right? That's the double angle identity. And then plus sine squared theta minus 1/4 equals 0. Now it's all in theta. The second step is to get one trig function. Right? And then you can solve it. Maybe it's a linear equation, maybe it's a quadratic equation, some kind of algebraic equation for a trig function, and from there go to the unit circle. Well, I want to get one trig function I can. When I see sine squared, replace it with 1 minus cosine squared in both these cases and get it in terms of cosine only. However, in this case, it's even easier. Minus sine squared and plus sine squared cancel. If they didn't, though, I can use the Pythagorean identity. Instead of sine squared, write 1 minus cosine squared, or instead of cosine squared, put 1 minus sine squared. Either way, we'll get it to one trig function. Once I have that, you can solve for the trig function algebraically. For this class, it's by algebra. It might be in general anything, but mostly it's algebra in any case. If I have cosine squared minus a fourth equals 0, what I can do is let u equal cosine x, cosine theta. And then this becomes u squared, these canceled, minus a fourth equals 0. Oh, it's a quadratic equation. I can always solve this with the quadratic formula, which you should know. So we'll say e.g., meaning, for example, by quadratic formula or factoring. Or maybe it's just easy. Maybe it's linear. Just add b and divide, subtract b and divide by a. Yeah.
What did you do to get rid of the sign?
Oh, it just, when I replace cosine 2 theta with cosine squared minus sine squared, the minus sine squared canceled the plus sine squared that came down from here. So it's just lucky, but if it can cancel, I could replace sine squared with 1 minus cosine squared. That would. All right, so I've got this equation. Now I recognize it's a quadratic equation. I can use the quadratic formula if I want, but what's easier here? Factoring, for instance, right? I could call this u plus a half times u minus a half using algebra, right? You can think of this u squared minus a half squared. Difference of squares, u plus a times u minus a. There it is, and now I observe by the zero product formula that if this product is 0, then either this is 0 or this is 0. U must be minus a half to make this one 0, or u equals plus a half to make this one 0. There it is. But you follow this set of rules. And now I have u equals a half or u equals minus a half. That is cosine theta equals a half minus a half, or cosine theta equals plus a half. So that's what you can do. Now, once you've got, this is to get trig function equal a number. Look familiar, hopefully. Once you've got trig function equal a number, you solve it on the unit circle, right? Which, if it's a nasty angle, you solve it in terms of inverse trig functions, but if it's a special angle, you can figure it out, right, by hand. So solve on the unit circle. That's it. 0, 1, 2, 3 here. Solve on unit circle. So with this one, cosine theta is the x-coordinate of the unit circle. So I want all points with x-coordinate equal minus a half. Here's minus 1. Here's halfway in is minus a half. And I notice there's this line will cut the circle through its interior at exactly 2 places. So there will be exactly 2 possible terminal rays such that the x-coordinate of the unit circle is minus a half. Now, the other possibility is cosine theta equals plus a half. That's x equals a half, is this vertical line halfway to 1. Once again, there's 2 points at which the unit circle is cut by the vertical line. So there's 2 angles here. Now, what are those? I can figure them out easily, right? If this goes over 0 to minus a half, then the length of this side is plus a half. This is 1 because it's a unit circle. The Pythagorean theorem will determine that this side must be square root 3 over 2. You don't even have to do that, though. Once you see the 1/2 and 1, you know it's a 30, 60, 90 triangle with this one equal to 60 degrees. Right? Well, let's cut right in radians. Assuming we're solving this in radians, pi over 3. And now what's the angle that gets you here? Pi back up pi over 3. So one solution is to say theta equals pi back over pi over 3. Plus pi minus a third pi is 2/3 pi, right? That's one angle. Then this angle here, well, if this is pi over 3, by symmetry, this will be pi over 3. That symmetry always comes through in these problems. You can always drop the perpendicular and see it. Oh, this is a half and this is 1, same thing, same triangle. Well, this is pi plus pi over 3. 1 pi and a third pi is 4/3 pi, right? So there's two solutions to this one. Theta equals 2 pi over 3 or 4 pi over 3. Then we have to do this one. Since we dropped it to, with the line x equals plus a half, this must be a half, which makes this side length here a half. This is 1. Again, it's a 30, 60, 90 triangle. That's 60 degrees, pi over 3. As you can see, you need to know both radians and degrees for this test, right? So pi over 3, let's put it in red again, just to be consistent. Theta equals pi over 3 because it's a 1/2, 1 square root 3 over 2 triangle. Then you can have this one. By symmetry, this angle must also be pi over 3. It also goes over half a unit and 1 out here. So I have 2 pi back up pi over 3 for this angle. Then you have to use your fractions, right? 2 pi multiplied top and bottom by 3 gives you 6 pi over 3. Subtract pi over 3 means you subtract the numerator. 6 pi minus pi is 5 pi all over 3, right? So the difference in the numerators over the common denominator. So I have two more angles here. Pi over 3, 5 pi over 3. Those are all the angles between 0 and 2 pi. What are all angles? I didn't say all angles between 0 and 2 pi. If I want all angles, what do I put? So this is the answer if I say 0 to 2 pi, that's all of them. But for all angles, you put all coterminal angles. So plus 2k pi to each where k is any integer. Okay? Here's that one. Feel good about that one? Can you do these steps? But hopefully this reinforces all the stuff we learned on solving trig equations. They come up a lot in the sciences. Let me make sure I do this one because I think this is the hardest problem. And then I want to make sure if you've got some you've been looking at, waiting to look, see here. Number 18. Find cube roots, that is the third root, of negative I. What three complex numbers cubed will give me negative I? Remember what we said before is if you want nth roots, there's n of them in complex numbers. That's the general rule, and you can see it from the formula. If you want fourth roots, there's 4 of them. Fifth roots, there's 5 of them. What are the 4 roots of this one? Well, you can rewrite it like this. This is 0 plus negative 1i written out. So it's a plus bi. What are all numbers that do that? What you do is remember in arithmetic, you can use the standard form easily, but for powers and roots, you want to use the polar form. So let's, in polar form, if I write z equals r cosine plus I sine theta, what we're asking for is z cubed equals minus I to be written as, what's z cubed? If z is this, then r psi theta cubed must be equal to minus I. What's minus I in polar form? Remember that? You can figure it in an easy way like this. Where's minus I in the complex x plus y plane, right? Z equals x plus iy. Well, it's x equals 0, y equals negative 1, right? 0 plus negative 1i. So I go 0 horizontally and negative 1 vertically. It's right here, negative 1. That's where I put minus I. Right? So negative I is this point right here. You can figure it's it's 1 unit from the origin, so r equals 1, right? R is always the distance from the origin. And the angle around here is theta equals 3 pi over 2, right? Pi over 2, pi, 3 pi over 2. And so this one, written in its polar form, is r1 times cosine plus I sine of the angle, 3 pi over 2. Now, if it's not such an obvious one, I know where to plot minus I, maybe it's 5 minus 6i or something like that. I can always compute it like this. R is the square root of x squared plus y squared, without the I in here. It's 0 squared plus minus 1 squared, not minus I squared. The square root of 1 is 1, so that you can get R that way too. You can look at the picture, so it's 1 unit from the origin or computed. And then tangent theta equals y over x is minus 1 over 0. That one normally works, but when it's on the x-axis here, you just have to look at it. So this one tells you since x is 0, it has to be pi over 2 or 3 pi over 2. Look on it and see it's 3 pi over 2. So you can figure it that way also, but the picture is easiest in this case. All right, now here's the big trick though. When finding roots, you also say this is one angle that gets there, but it's also plus any 2k pi is the same direction, right? Put all the possible angles in, including all the coterminal angles that there are, right? So now let's write it that way. If you write z cubed equals r times size angle plus 2k pi, you can solve that for all the cube roots, right? Cube root, we want its cube to be minus I. Well, this by de Moivre's theorem is r cubed, you cube the distance from the origin, size 3 theta. You multiply the angle by the power. Right? Cube of any complex number is r cubed size 3 theta. And then this one you can leave the same, 1 times size 3 pi over 2 plus 2k pi. And for those complex numbers to be equal, you need r cubed equal 1. You need the same radius from the origin. And you need the same angle here within 2k pi with the coterminal angles. So we need r cubed equals 1. And we need 3 theta equals 3 pi over 2 plus 2k pi. Well, r is the real number distance. Its cube root is 1, so r has to be 1. Real cube root of 1. And then theta, by dividing both sides by 3 here, is pi over 2, 1/3 this one, plus 1/3 this one, 2k pi over 3. There's the r and theta for all cube roots of negative I. Now, k can be any integer, right? But we only keep certain ones of them. Remember which ones we keep? We can keep 0, that gives you one angle, it's pi over 2, right? So pi over 2 is one angle. Put k equals 1, you get pi over 2 plus 2 pi over 3, that's another one. Put k equals 2, you get pi over 2 plus 4 pi over 3, that's another one. But if you put k bigger, like you put k equals 3, 2 times 3 pi over 3 is 2 pi, and it's the same direction as pi over 2, you don't need that one, it's the same as 0. Put k equals 4, and it's the same direction as when you put in 1, put in 5, it's the same direction when you put in 2. So these are the only way you get different directions. You can put in any k, that all works, but the only different directions come from 0, 1, and 2. So for cube roots, you get exactly 3 angles. For fourth roots, you'll get exactly 4 different directions, and so on. Hence, the cube roots are z equals r cosine plus I sine theta with k equals 0 is pi over 2 plus 0. This is the k equals 0 solution. Z equals R times cosine plus I sine pi over 2 plus, when you put a k equals 1, it's 2/3 pi. That's what you get when you put k equals 1. And Z equals R cosine plus I sine pi over 2 plus, putting k equals 2, you get 4 pi over 3. And after that, you get repeated numbers. So these are the three cube roots in polar form. This one is k equals 2. So this is the answer on the homework. I'll take that on the test. That's the polar form. Polar form. Cube roots are these. It's kind of fun to figure out what they are in rectangular form. You don't need to do this for the exam. I said you can leave them in polar form because that's what the homework did. But for instance, what is this number if you put it in its standard form? What is that number? Well, this means 1 times cosine pi over 2 plus I sine pi over 2, right? You just figure it out. Cosine pi over 2 is 0. Sine pi over 2 is 1. Oh, it's 1. 1 times 0 plus I, it's I. I is a cube root of minus I. How about that? You can see it if you multiply it. Check. All right. I cubed is I squared times I is minus 1 times I, because I squared is minus 1, is minus I. Sure enough, I is a cube root of minus I. And you can do these two. They're not too bad. In fact, you can figure them on the unit circle. Here's how it works. Minus I was down here at 3 pi over 2. This is beyond what I'm going to ask you on the test, but just for your education. The first angle is 1/3 of that angle for a cube root. It goes pi over 2. And the other two are symmetrically placed here and here. Each one 1/3 of the way around the circle. 2 pi over 3, 2 pi over 3, 2 pi over 3. Here. But for three roots, the first one is 1/3 of the angle of the original number minus I. So if this is 3 pi over 2, the first root is pi over 2. And the other two are symmetrically placed on the circle of the same radius. And so you get this number, I is 1, 0. And this, if you figure it out using the triangle, is minus square root 3 over 2 plus 1/2 I, because you have minus square root 3 over 2 and minus a half here. And this one, square root 3 over 2 and minus a half is square root 3 over 2. This is minus a half I, sorry. Square root 3 over 2 minus a half I for this one. So this number cubed gives negative I, this number cubed gives negative I, and this number cubed gives negative I. It's got a very pretty picture when you figure these out. They're symmetrically placed in the complex plane, x plus I, y. But just leave it like this. R size angle, R size angle, R size angle. That's good. That's the trickiest one I can ask you on the test. Any questions on that one? That one's kind of hard. But if you know that, you know all the complex numbers. We actually use these in differential equations to solve real world problems. Pretty amazing. You use imaginary numbers to get real results, I think. Okay, well, it looked like I wore you out with that one. Anything that you want to look at in particular? I've been looking at some of those problems. I'll pick some others if you don't have any suggestions. What else would you like to look at on here? Yeah.
On number 22, when you say find the angular frequency,
Yeah.
the same as the speed.
Yeah, good point, because we just mentioned this in passing, and I need to do a better job with this. You'll like this one because it's easy too, right? Find the angular frequency which really isn't in a lot of trig books, and yet when you go into a course where you apply it, it's always in there. I can't understand why they don't emphasize it more in trig books. All my science classes, you had to know this, but they don't present it real carefully. It is there, but it's not spelled out carefully. And period of y equals 6 cosine pi x. What you do is you rewrite this in the a cosine bx minus c plus d form. 6 cosine pi x minus 0 plus 0. Right? So here's a, b, c, and d. The period you already know. What's the period for a cosine? From the other problem. Pi over b, yeah. So it's 2 pi over pi. This one has period 2. So that's the period. What's the frequency? This is what needs to be emphasized as not. It's very easy. The frequency is always 1 over the period. It's the reciprocal. You just take 1/2. How about that? Easy as that. So memorize this. Frequency is 1 over the period. Period you already know from previous is 2 pi over. And then the angular frequency, sometimes called omega, actually is even easier. It's b. I wish they'd say that in the books. That's what I said in Buckman. It's right there. It's looking at you. Pi, right? B is pi, so it's pi. You also say it's 2 pi times the frequency. That's the other way to compute it. But period is 2 pi over b. The frequency is the reciprocal of the period, and omega is just b. The angular frequency is just b. So that's what you have. 2, 1/2, and pi are the answers. Easy as that. Even though we didn't cover it real well because the book didn't. I want you to know that for your science class. In physics, I used to see that all the time. Frustrating when you didn't do well in trigonometry. Any others? That's a good question.
Page 24.
Again? Yeah, this is a good one too. We didn't do identities today. That's the other major point of the course, is to do identities and simplifications. Those come up a lot in applied courses everywhere. So here's 24, establish the identity. These, in this one, you're trying to show that sine 4 theta equals 4 sine theta cosine cubed theta minus sine cubed theta cosine theta. Right? The way to do these identities is write the two sides and work both ends towards the middle using these rules of thumbs that we had, where you try and get one angle by algebra, where you cancel common factors in the numerator and denominator, put things over a common denominator, that kind of stuff. And then you have trig identities you can put in. If you see sine squared plus cosine squared, you put 1, right? Trig identities. And then if you're stuck, what do we do? We wrote everything in terms of sine and cosine because the identities are easier to recognize there, right? So sine and cosine only. These 4 steps will get you through all the problems I might ask in here. Try to get one angle. Try algebra to simplify it. Try trigonometry to simplify it. If you can't, and you get stuck, put it right in terms of sine and cosine and try again. So here I notice I have theta, 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 but this is 4 theta. So first thing I want to do is get rid of that 4 theta. I don't have a quadruple angle formula to reduce that. So how can I reduce that to be theta like these other ones? I can't do anything until I get it there. In fact, what this is a quadruple angle identity, right? I'm finding this is a quadruple angle formula, if you like. But you don't memorize those. There's too many, right? But you can figure them out when you need to. That's the idea, using your other identity. What you do is I say, well, I know I could write this as twice 2 theta, right? The double angle. Now I can use the double angle formula that I do know, right? If I call alpha equal 2 theta, then this is sine 2 alpha. And the double angle formula, sine 2 alpha is 2 sine alpha cosine alpha, right? Where alpha is 2 theta. So I'm halfway there. Now I've got 2 theta instead of 4 theta. Now I just use the double angle the formulas for sine and cosine here. Double angle again, sine of 2 theta is 2 sine theta cosine theta, right? My memorization. This becomes the sine 2 theta. And then cosine 2 theta, you remember, is cosine squared minus sine squared. This. So this is equal to this, this is equal to this, this is equal to this. Finally, at last, all in terms of theta. Now what do? I'm going to try algebra. I don't see anything to cancel. I don't see any making a common denominator. I don't see any easy trig identities there. I guess I could write cosine squared as 1 minus sine squared, or sine squared as 1 minus cosine squared, but it doesn't seem to make it easier. Wait a minute. And it's already in terms of sine and cosine only, right? But wait a minute, if I just multiply this out, 2 times 2 is 4. And if I multiply out, right, I'll take A times B minus C, AB, oops, forget the 2, sorry. If I call it A times B minus A times C, right, when you multiply this out, this times this is sine times cosine cubed, that's that one. This times this is sine cubed times cosine, that's that one. Oh, it's just multiply out. There it is. So that's the whole derivation. And what I want for the problem is just these intermediate steps. It's a proof, right? You put these steps to show how you can find identities go from here to here. But it's just the double angle formula twice, you get it in terms of one angle. And then, had you had more of a mess in there, maybe use trig identities in algebra. I won't give you anything harder than that. I don't want to make this too terribly awful, but just, if you know your double angle identities, you can do that in simple proof, hopefully. The actual test will be much shorter than the practice test. This is too many problems. And again, this score will replace your lowest score. So if you do worse, it won't lower your grade. This will be the one that's dropped. Anything else we should look at? Let's look at 28C. We didn't do polar coordinates. Suppose I said convert to polar coordinates. Well, if I've got 2 sine theta plus cosine, not polar coordinates, the rectangular coordinates, sorry, rectangular coordinates from polar coordinates. 2 sine theta plus cosine theta equals 0. How do we convert these polar coordinates to rectangular coordinate equations? Remember this? Ideally, what you want to do is just memorize those 4 equations. X equals r cosine theta, y equals r sine theta, r squared equals x squared plus y squared, and tangent theta equals y over x. Whenever you see one of these things, this, or this, you replace it with the rectangular form. I don't see any of those there, so what am I going to do? Try and make it so. Maybe you square both sides, you multiply through by r, or something like that, divide. Here's an idea. I can multiply this through by r and write it as 2r sine theta plus r cosine theta equals r times 0 is still 0. So multiply by r, because now I see r sine theta and r cosine theta. That's what's in my equations. So you try and get what's in here, and then you can substitute directly. X replaces r cosine theta. Y replaces r sine theta. Oh, look at that. It's just x plus 2y equals 0. This is ax plus by equals c. It's a line in general form, right? Ax plus by equals c with a and b not both 0 is the general form of a line. you can leave it like that. There it is converted. You can sketch it also. Did I say sketch on that one? I can't remember. No, I didn't say sketch. So since I didn't say sketch here, I won't ask you that on the final either. Just leave it here. But you can sketch this, plot 2 points and put your straight edge down, easy, right? Or write it y equals mx plus b form or something. The other one, some of them we just did in the last test, and unless you ask, I won't do them again. Remember, the answers are all in the back, so you can check and see if you're doing it right. Don't see me. You want to work out some of these for you. I guess, why don't we do 27? We haven't done enough with complex numbers. What is 2 plus 2 square root 3i to the 6th power? Compute that and write it in standard form, z equals x plus iy. How can I do powers? Remember? You just do arithmetic, you don't need polar form, but for powers and roots, you use polar form. So I first find r is square root x squared plus y squared, where x is the real part and y is the imaginary part, the number multiplying I. So this is square root of 2 squared plus 2 square root 3 squared. Well, let's see, 4 plus 12 is 16, square root of 16 is 4. So this point is actually exactly 4 units from the origin. And now what's theta? Tangent theta equals y over x, 2 square root 3 over 2, square root 3. What angle is that? Square root 3 is probably a special angle, right? Well, if I write it as a quotient, square root 3 over 1, I'm solving tangent theta equals a number. I just solve it on the unit circle, right? That's what we said before. So I solve on the unit circle by converting this, divide top and bottom by the root sum square of those numbers. Square root of square root 3 squared plus 1 squared is 2. So I'll divide top and bottom by 2 and write this as square root of 3 over 2 over a half. Or I can take minus this over minus that. So on the unit circle, this is y and this is x, or this is y and this is x. So I can solve this on the unit circle as x is y is square root 3 over 2, x is a half. This point, or the opposite one, both negative. Down here, minus square root 3 over 2, minus a half. Which one is it? It has to be the same quadrant as the original number. X positive and y positive, so it's this one. And I notice 1/2 square root 3 over 2, this is pi over 3. So the angle theta is pi over 3, the one in the same quadrant as the original point, x and y both positive. So it has this tangent. So now what I'm going to do is I'm going to say that 2 plus 2 square root 3i to the 6th power can be done in polar form as r cosine plus I sine theta to the 6th, where r is 4 and theta is pi over 3. What's the 6th power of a complex number in polar form? R psi theta. You take r to the power and you multiply the angle by the power. So it's 4 to the 6th psi 6 times pi over 3. This is 4 to the 6th, which you can also write as 2 to the 12th, that's easier. This is 4,096, I think, if you take 4 to the 6th. Yeah. So it's 4,096 if you do it in your calculator times cosine plus I sine of 2 pi, right? What is that? Cosine 2 pi plus I sine 2 pi. Cosine is 1. Sine of 2 pi is 0. It's just 1. So this is 4,096 times 1. It's 4,096. How about that? This is 1 plus 0i. This one is number 1. All right, so, boy, you take this two plus two square root of 3 I to the 6th power, you actually get 4,096, a real number. Don't let that. Well, that runs us out of time. Come down to my office hour, if you want to ask some more questions, I'll be happy to answer some more, and best wishes to all of you on the final. Thank you for a really great semester.